Hello YouTube! I intend to make a series/playlist of university-style bachelor-level video lectures, where I go through the linear algebra textbook by Sheldon Axler, Linear Algebra Done Right. Here's the cover of the book. So this is the first video in that series where we will go over complex numbers in an introductory level of depth. So without further ado, let's get started. Chapter 1.1, Complex Numbers. So, why do we need complex numbers? Well, consider the following equation. X squared equals minus 1. And we ask ourselves, does there exist any real number such that its square is equal to minus 1? Well, since for all real numbers the square is non-negative, there does not exist a real solution to this equation. So, written in a mathematically formal, logically formal notation, we have that for all x belonging to the set of real numbers, x squared is greater than or equal to than 0. So it follows that there does not exist an x belonging to the set of real numbers such that x squared is equal to minus 1. So this equation has no solution. Sad. So how do we solve this issue? Well, we just invent new numbers and expand our toolbox so we can solve equations of this form. And that's what we're going to do now. So let's expand our toolbox in the following way. We will assume that there exists a number which we will call the imaginary unit, denoted as such, and the defining property that we demand this number have is the following. I squared is equal to minus 1. So we're just outright assuming that there exists a number I such that it satisfies the equation we've seen before, which we could not solve using the real numbers. And now that we have I at our disposal, we can define this new type of numbers, complex numbers. So a complex number is a number of the following form, a plus b times I, where a and b are real numbers. So how to think about these numbers, how to visualize them? Well, real numbers are one-dimensional numbers. They lie on the real number line. And to expand this picture, to make room for the complex number, so we just add this imaginary axis, which is perpendicular to the real numbers, and on it lives I over here. And now, for example, if we have the complex number 1 plus 2i, well, 1 is its real part, so we go 1 unit to the right, and 2 is its imaginary part, so we go 2 units up, and we land at this point over here, which corresponds to this complex number. So complex numbers are two-dimensional numbers. Now, these numbers that we've just defined, they're a new sort of object, a new sort of number, and we currently don't know how to add or multiply these numbers. So we will have to figure out how to define addition and multiplication in a meaningful manner. To accomplish that, we will proceed in the following manner. So to figure out how to define addition, let's say we have two complex numbers and we want to add them. And we're trying to figure out what should this mean. Well, let's just assume that the number I behaves nicely, for we want at the end these complex numbers to behave as nicely as the real numbers. So we will get rid of the parentheses and I will group terms. So a and c will go together. I'll put parentheses around them. And since I'm assuming that, well, since I'm demanding that the I behaves nicely, that means that it should obey the law of distributivity. So I can pull out the I from here and group these terms together. And then we end up with this complex number where its real part is a plus c and its imaginary part is b plus d. So we got this, And we will use this to define addition. So what does it mean to add two complex numbers? Well, it is to get this new complex number, which you compute in this manner. Same for multiplication. Let's just do normal multiplication, like with the real numbers, and see what we get. So a times c, a times di, b times I times c, and b times I times d times I. So we get this, and in the last term we have b times d times I squared. And recall, I squared is equal to -1. So we use that fact, and now we get this expression, and now we just group terms again like we did with addition. So this is the real part of this new complex number, and this is the imaginary part of this new complex number. So we have this, and we will use it to define multiplication. So what does it mean to multiply two complex numbers? Well, it's to get this new complex number using this computation. This is how you multiply complex numbers. So the above expansion of our toolbox was done in a informal, naive manner where we just assumed that something like the imaginary unit exists. But now I would like to actually construct a mathematical object that will perform the role of the imaginary unit. So to achieve that construction, we will have to introduce the concept of a set, and informally, a set is a collection of things. Think of a bag or a box or any other sort of container. Formally, a set is a primitive term. It does not have a definition per se, but only defining features that we call axioms. So we'll just proceed using the informal notion of a set, using our intuition. Another concept we will need is the concept of x belonging to a set S. So this we also do not define. It is primitive. We just intuitively understand what it means for something to, well, be in a box, to belong to a set. So this reads x is an element of S. Now, to define what it means for x to not be an element of S, well, we just use the concept of x belonging to S and just negate it. So this is the symbol for logical negation. So here's an example. Here's a set A. Here are its elements. So we have 0, we have cat, we have this poorly drawn sun, we have your mom. So your mom belongs to A, while this banana or poorly drawn crescent moon does not belong to A. And here's a visual representation of set S. And if I take an element x, which is inside of S, well, then x belongs to S. And if I take an element which is outside of S, well, then y does not belong to S. Now we would like to define the concept of a subset, but before we get to the definition, I would like to introduce some motivation. So here we have two pictures. Here is a set x and a set y, and set y is fully contained within x. So since y is fully contained in x, whatever element little y I pick that is within big Y, it will also be an element of x. So this little y is contained in big Y, but it's also contained within x due to big Y being fully contained within x. So in this situation, this implication holds for whatever little I choose from big Y. But in this picture, x and y have some overlap. So this little y belongs to y, and it also belongs to x. But not all elements of y belong to x. So this y prim over here belongs to y, but it does not belong to x. So the implication that held in this picture for all elements y of my set y does not hold for this picture. So this picture over here is going to serve as our motivation for the following definition. We say that A is a subset of B if and only if this implication is true. So if this implication is true, if I take an element x belonging to A, then I can safely conclude that x also belongs to B. So this is what it means for A to be a subset of B. It is for this implication to hold. So here are some examples. Here's the set of natural numbers. Here's the set of even integers, of even natural numbers. And the set of even natural numbers is a subset of the natural numbers, whilst the set of natural numbers is not a subset of the even natural numbers. We also have that whatever set x you might take, x is a subset of x, so every set contains itself, and this little fellow over here, the empty set, the set with no elements, is also a subset of any set x, due to logical reasons, due to the nature of how implications are evaluated for their truth or falseness. Now we would like to define what it means for two sets to be equal. Again, some motivation. So this is in this picture, B is a subset of A, and in this picture, A is a subset of B. Now, if both of these were to hold, the only reasonable picture we could expect to conceive of would be this picture, where A and B overlap. So A is equal to B, analogous to numbers and the relation less than or equal to. For if x is less than or equal to than y, and y is less than or equal to than x, then it follows that x is equal to y. Hence we have the following definition of equality for sets. A is equal to B if and only if A is a subset of B and B is a subset of A. So two sets are equal if and only if they have the same elements. So some consequences of the definition of equality are the following. Here we have what seem to be two different sets, a set containing x once and a set containing x 5 times. But due to the definition of equality, they have the same elements, namely x, so these two sets are equal. Also, the set containing AB is equal to the set containing BA. So, as we can see, sets do not care about repetition of elements, nor do they care about the ordering of elements. Those concepts are not encoded in sets. But for our purposes, we will need a container that does have the notion of ordering, so we can tell what the first element is and what the second element is. So, to accomplish that, we define the following object called an ordered pair. So this is the ordered pair AB. Here is how it's defined. What does it mean for AB to be an ordered pair? Well, it means to be this set over here. Now, the point of this definition is to, using sets, construct an object which does have a notion of ordering, and this definition accomplishes that. So now we have that in general. The ordered pair AB is different from the ordered pair BA. So here's an example. The ordered pair 3, 4 is different from the ordered pair 4, 3 because these two sets are not equal. This is the only element they share, and this set over here has this element, whilst this set has this element, so they're not equal, hence the ordered pairs are not equal. And we have what we wanted. This is different from this, so order does matter in ordered pairs, hence the name. So for an ordered pair AB, we say that A is the first element and B the second element. Now we shall prove the following. We shall prove that if A and B, the ordered pair A and B is equal to the ordered pair C and D, well, that is the same as their coordinates being the same. So what does it mean for two ordered pairs to be equal? It means that they have the same corresponding coordinates elements, first elements and second elements. So as we can see, equality is not something we have to define for ordered pairs, but instead it is a direct result of the definition of an ordered pair. It is something we derive and prove. So in this case, two ordered pairs are equal if and only if their corresponding elements' coordinates are equal. So to prove this, we will have to prove two implications. We will have to show that the left-hand side implies the right-hand side and that the right-hand side implies the left-hand side. Well, let's go from right to left. So if we suppose that A is equal to C and B is equal to D, well then the ordered pair AB is just equal to the ordered pair CD. I can just replace A by C and B by D. So the right-hand side does imply the left-hand side. Now let's go from left to right. So we assume that these two ordered pairs are equal. That means that these two sets are equal. Now there are two cases to consider. I'll just go through the first. So since these two sets are equal, that means that, for example, this element over here is equal to this element, and this element has to be equal to this element. So we have that the set containing A is equal to the set containing C, and the set containing AB is equal to the set containing CD. So since these two sets are equal, we get that A is equal to C. And now, using the fact that A is equal to C and this equality over here, we get that the set CB is equal to the sets which contain CD. So now we get that B is equal to D. Analogous, the second case, now we just have to suppose that this element might be actually equal to this element, and this element is equal to this element. So, but the point of the proof is the same, and you get that A is equal to C and B is equal to D. So we've shown that the left-hand side does imply the right-hand side. End of proof. Now we can define the complex numbers in a satisfactory manner. So complex numbers, which we will write as A plus B times I, will be actually ordered pairs of real numbers. So this complex number over here is actually this ordered pair of real numbers. And we will also perform the following identification. So we will consider every real number. We will identify it with this complex number over here, A plus 0 times I. This enables us to consider the real numbers as a subset of the complex numbers. So now we can see what the imaginary unit I truly is. So I is equal to, well, we write it out in the form of A plus B times I. So A is 0, B is 1. So we get that I is actually equal to this ordered pair over here. And now, using our previous derivations of the definitions of addition and multiplication, we can define addition and multiplication for our ordered pairs. That is, for our complex numbers defined this way. So we take two complex numbers, C and W, so these are the following ordered pairs, and we define the C plus W to be equal to this ordered pair, using this as our inspiration, and C times W to be equal to this ordered pair, using this result, this previous definition, as inspiration. And now let's check whether our imaginary unit truly does the job of an imaginary unit. So we ask ourselves, is I squared equals to minus 1? Well, I squared is equal to I times I, which is equal to this ordered pair times this ordered pair. And now, using our definition of multiplication, we can, well, multiply these two ordered pairs, these two complex numbers, to arrive at the following result. So I squared is equal to this ordered pair. So we write out that I squared is equal to this ordered pair, and now we write this in the form of a plus b times I. So we get minus 1 plus 0 times I, which we identify with the real number minus 1. So I squared is equal to minus 1, which is what we wanted of our imaginary unit. So we have constructed a mathematical object, this ordered pair, which acts as the imaginary unit. And now we can just declare the complex numbers to be the set of all complex numbers is just the set of all of these ordered pairs written out as this expression here. So these are the complex numbers. Due to the nature of the real numbers and our definitions, the complex numbers behave super nicely. Multiplication and addition are commutative, we have associativity, we have our unique 0 and unique 1 for the neutral elements when it comes to addition and multiplication. We have our additive inverses, and we have our multiplicative inverses, and we have this distributive property. All of these you can derive using, well, the properties of real numbers and the definitions we've given for complex numbers. So since we have unique additive inverses, we can define subtraction in the following way. Subtraction is really just addition, where we just add the corresponding additive inverse. And division is really just multiplication by the corresponding multiplicative inverse. In this case, we take the multiplicative inverse of z, which we write like this fraction over here, and just multiply it with w. This is what division is.